Imagine waking inside a gleaming dome city on Mars, sunlight filtering amber through transparent walls, gardens stretching beneath artificial skies. Children run between hydroponic towers. Engineers tend fusion reactors humming with life. Outside, rovers carve pathways through red dust, under a sky the color of rust and hope. This is the dream we have been sold, the vision of humanity's future, written in conference halls, splashed across billboards, whispered in the quiet promises of billionaires who speak of making life multiplanetary. But now imagine something else. Imagine waking to alarms, air recyclers failing, radiation levels climbing, the dome's structural seals weakening under relentless atmospheric pressure differentials, crops withering despite every technological intervention, and slowly, with the patience of geology itself, the realization settles in. The colony is dying, not from accident or oversight, but from physics, from chemistry, from the immutable laws that govern worlds. This is the uncomfortable truth scientists whisper about in labs late at night, the reality buried beneath renderings of Martian cities and speeches about human destiny among the stars. Tonight, we journey not to celebrate Mars, but to examine it, to ask the questions that marketing campaigns avoid and engineering optimism often overlooks. Can we truly terraform Mars? Or have we fallen in love with an impossibility? For over a century, Mars has captured human imagination like no other world. From H.G. Wells's Martian Invaders to Ray Bradbury's Chronicles of Colonization, from the Viking landers to Curiosity's tire tracks in ancient riverbeds, we have projected our hopes onto this rusty neighbor. In recent decades, that dream has crystallized into mission statements and timelines. Space agencies plan habitats. Billionaires promise tickets. Children draw pictures of Martian cities in classrooms across Earth, believing they might one day walk beneath that salmon sky. The promise is magnificent. Make Mars livable, thicken its atmosphere, warm its frozen surface, melt its polar ice, plant forests in Valles Marineris, build oceans in Hellas Basin, transform a dead world into a second home, a backup plan for humanity, a testament to our ingenuity and refusal to be confined to a single fragile planet. But what if the promise is built on sand? What if the physics simply don't allow it? What if Mars, for all its proximity and familiarity, is fundamentally inhospitable in ways we cannot engineer around? Not with current technology, not with future breakthroughs, perhaps not ever. Before we continue, I'd love to know where you're watching from right now and what time it is in your corner of the world. Drop a comment below. Are you drifting off to sleep under city lights or waking to a quiet morning? Wherever you are, we're glad you're here, journeying with us through these cosmic questions. Tonight, we will explore 8 fundamental barriers that stand between humanity and a living Mars. We will examine the atmosphere it cannot hold, the cold it cannot escape, the radiation it cannot shield against. We will look at water that exists but cannot flow, soil that poisons rather than nourishes, and gravity too weak to sustain human bodies over generations. We will ask where the materials for terraforming would even come from, and whether we have been focusing our dreams and resources on the wrong solution entirely. This is not a story of defeat, but of clarity, of understanding our solar system as it truly is, not as we wish it to be. So settle in. Let your thoughts drift toward the red planet hanging in our night sky, and prepare to see Mars not through the lens of hope alone, but through the patient, unforgiving light of physics. Let us begin with the air, or rather, the absence of it. When we imagine terraforming Mars, the first vision that comes to mind is one of breathable air, of walking across red deserts without a helmet, feeling the wind on our face. But this dream collides immediately with the most fundamental obstacle, one that cannot be overcome with technology or determination. Mars cannot hold an atmosphere. Not now, not in a century. Not even if we poured every gas we could extract from every comet in the solar system onto its surface. The current atmospheric pressure on Mars is less than 1% of Earth's. To understand what this means, imagine standing at the summit of Mount Everest, where the air is so thin that every breath is a struggle, where without supplemental oxygen, your body slowly begins to fail. Now imagine an atmosphere 16 times thinner than that. This is Mars. Even on its deepest valley floors, where the pressure is at its maximum, the air is barely there at all. Your blood would boil, not from heat, but from the vacuum. Your lungs would collapse trying to extract oxygen from a gas so sparse it might as well be space itself. But here is the deeper, more troubling truth. Even if we succeeded in manufacturing an atmosphere, even if we released billions of tons of greenhouse gases, melted the polar ice caps, and transformed Mars's sky from pink to blue, it would not last. The atmosphere would not simply dissipate slowly over eons. It would be actively torn away, molecule by molecule, day after day, by the relentless force of the sun itself. This is not speculation. This is what happened to Mars in its ancient past. And it is what continues to happen today. Billions of years ago, Mars was not the frozen desert we see now. Evidence from Martian geology, from dry river valleys carved into bedrock, from minerals that only form in the presence of liquid water, tells us that Mars once possessed a thick atmosphere, dense enough to trap heat, warm enough to allow rivers to flow across its surface. For a brief moment in the planet's youth, Mars may have resembled Earth, a world of clouds and rain, of lakes reflecting a young sun. But then, something catastrophic happened. Mars's magnetic field died. Deep within Earth, a churning ocean of molten iron generates a powerful magnetic field that extends thousands of miles into space, creating an invisible shield called the magnetosphere. This shield deflects the solar wind, a continuous stream of charged particles that erupts from the sun at speeds exceeding 1 million miles per hour. Without this protection, the solar wind would bombard Earth's atmosphere directly, stripping away oxygen, nitrogen, and water vapor, molecule by molecule, until nothing remained. Mars once had such a field, but approximately 4 billion years ago, its core cooled and solidified. The dynamo effect ceased, the magnetic field collapsed, and Mars stood naked before the fury of the sun. What followed was not instantaneous, but it was inevitable. The solar wind, no longer deflected, began to strike the Martian atmosphere directly. High-energy particles collided with atmospheric molecules, transferring energy and momentum, sending lighter gases spiraling away into space. Over millions of years, the atmosphere thinned, temperatures dropped, water froze or evaporated into the void. Mars transformed from a world that might have cradled life into a barren, radiation-scorched wasteland. And this process has never stopped. NASA's MAVEN spacecraft, which has orbited Mars since 2014, has directly measured this atmospheric stripping in real time. Every second, approximately 100 grams of atmosphere escapes from Mars into space. Every day, Tons of gas are lost. Every year, the atmosphere grows imperceptibly thinner. On geological timescales, even the thin atmosphere that remains is temporary. Mars is bleeding into space, and nothing can stop it. This is the fundamental problem with terraforming Mars. It is not merely a question of adding atmosphere. It is a question of sustaining it against a force that has been eroding Mars for billions of years and will continue for billions more. Consider Venus, a planet often compared to Mars in terraforming discussions. Venus is closer to the Sun than Earth, subjected to even more intense solar radiation. Yet Venus possesses an atmosphere 90 times thicker than Earth's, a crushing envelope of carbon dioxide and sulfuric acid clouds that has persisted for eons. Why? Because Venus retained its internal heat. Its core remains partially molten, generating weak magnetic fields and, more importantly, continuous volcanic outgassing that replenishes atmospheric losses. Venus loses atmosphere to the solar wind, but it replaces what it loses. Mars has no such mechanism. Its volcanoes have been silent for hundreds of millions of years. Its core is cold and dead. There is no replenishment, only loss. Some have proposed solutions. Build an artificial magnetic field, they say. Position a massive electromagnetic shield at Mars's L1 Lagrange point, the gravitational balance point between Mars and the Sun, creating a protective bubble that deflects the solar wind just as Earth's magnetosphere does. It sounds elegant in theory, but the reality is staggering. To generate a magnetic field strong enough to shield an entire planet would require a structure of unprecedented scale and power. Current estimates suggest a magnetic field strength of several Teslas would be needed, sustained continuously across a region thousands of miles wide. The energy requirements would be equivalent to the total power output of multiple nuclear reactors running without interruption for centuries. We do not possess materials that could withstand the constant bombardment of solar radiation at that location. We have no power source compact and durable enough to function autonomously in deep space for the timescales required. And even if we built such a device, a single malfunction, a single failure of the power system, and Mars's fragile atmosphere would immediately resume its slow bleed into space. This is not a problem we can engineer around. It is a fundamental consequence of planetary physics. Mars is too small, too cold, and too dead to hold an atmosphere against the forces that govern our solar system. But even if we ignore these impossibilities, even if we assume we could somehow shield Mars from the solar wind, we must confront another question. Where would the atmosphere come from? To bring Mars's atmospheric pressure up to even 10% of Earth's, enough to eliminate the need for a full pressure suit, we would need to add approximately 1 quadrillion tons of gas. For comparison, the entire mass of Earth's atmosphere is about 5 quadrillion tons. We would need to manufacture or transport an Earth-equivalent atmosphere from somewhere in the solar system and release it onto Mars. The proposals are fantastical. Redirect comets from the outer solar system and crash them into Mars, releasing their water and frozen gases. Strip mine the moons of Jupiter for volatiles. Construct orbital factories to synthesize nitrogen and oxygen from Martian regolith. Each idea collapses under the weight of its own requirements. The energy to move a single comet into a collision course with Mars would dwarf the total energy humanity has ever produced. The industrial infrastructure needed to process Martian soil at the necessary scale would require resources we do not have and cannot obtain. And even if we succeeded, Even if through some miracle of engineering we managed to wrap Mars in a breathable atmosphere, it would not be permanent. The solar wind does not rest. The stripping would resume immediately. Within 10 million years, perhaps less, Mars would return to its current state. 10 million years may seem long by human standards, but in geological and cosmic terms, it is a blink, a breath, a moment. We would be building sandcastles at the edge of a rising tide. This is the atmosphere problem. Not a challenge to be solved, but a reality to be accepted. Mars cannot hold air. Its magnetic field is gone, and it will not return. The solar wind will strip away any atmosphere we create, no matter how much effort, energy, or resources we pour into the endeavor. We cannot terraform a planet that the sun itself is determined to keep barren. And this is only the beginning. The atmosphere problem is merely the first of many insurmountable obstacles. If we cannot give Mars breathable air, then every other dream of terraforming, every vision of oceans and forests, of rain falling on red soil, collapses before it begins. The foundations are not merely weak, they do not exist. As we turn our gaze toward the other challenges, temperature, radiation, water, soil, we begin to see a pattern emerge. Mars is not a world waiting to be awakened. It is a grave, silent and cold, marking the end of a planetary story that concluded billions of years ago. And no amount of human ambition can rewrite a tale already told by the cosmos itself. Beyond the thin veil of Mars's vanished atmosphere lies another truth, colder and more fundamental. Even if we could somehow restore the air above the red planet, we would still face an enemy that has gripped Mars for billions of years. An unrelenting planetary-scale deep freeze that no amount of human ingenuity can easily overcome. Mars is cold. Not simply cold in the way that winter is cold, or the way the polar regions of Earth are cold. Mars is cold in a way that penetrates to the very core of what makes a world habitable. The average temperature across its rust-coloured surface hovers around -63 degrees Celsius, -81 degrees Fahrenheit. At night, in winter, near the poles, temperatures plunge to -125 degrees Celsius, cold enough to freeze carbon dioxide itself out of the air into sheets of dry ice that coat the landscape like frost made of stone. Yet during brief moments in summer, near the equator, at noon, the thermometer might climb to a deceptively pleasant 20 degrees Celsius. This is not the sign of a world that is merely chilly. This is the mark of a planet trapped in thermal chaos, swinging wildly between temperature extremes with no moderating force to soften the transition. Distance from the sun plays a role, certainly. Mars orbits roughly 228 million kilometers from our star, half again as far as Earth. Sunlight arrives weakened, diluted across vast emptiness, carrying only 43% of the energy that bathes our own world. But distance alone does not explain Mars's frozen state. Venus, despite being closer to the sun than Earth, proves that distance is only part of the equation. What truly imprisons Mars in cold is the absence of something Earth possesses in abundance, an atmosphere thick enough to trap and hold the sun's warmth. Here we encounter one of the most vicious cycles in planetary science. To warm Mars, we need an atmosphere that can trap heat through the greenhouse effect. But to build and maintain that atmosphere, we need warmth, energy to release gases from the frozen soil, to keep molecules from escaping into space, to sustain chemical processes that would generate breathable air. Mars is caught in a feedback loop of its own making. Too cold to hold an atmosphere, too atmosphereless to retain heat. Each condition reinforces the other, creating a prison with walls made not of bars, but of thermodynamic inevitability. Terraforming advocates often speak of releasing Mars's trapped carbon dioxide, the CO2 locked away in polar ice caps and absorbed into the regolith beneath our feet. The idea sounds promising. Release enough greenhouse gas, the thinking goes, and Mars will begin to warm itself, triggering a cascade of atmospheric thickening that transforms the planet into a second Earth. But the mathematics of this dream are sobering. Scientists have calculated that even if we could release every molecule of accessible CO2 on Mars, every atom frozen in the ice, every trace absorbed in the soil, the resulting atmospheric pressure would increase by only about 20 millibars. The warming effect? Perhaps 10 degrees Celsius at most, maybe less. Mars would remain a frozen desert, merely a slightly less frozen desert, still far too cold and airless to support liquid water on its surface, let alone human life without extensive protection. The planet itself works against us in other ways. Mars's surface is highly reflective, possessing what scientists call a high albedo. The rusty dust that covers nearly everything, the exposed bedrock, the seasonal caps of frozen carbon dioxide, all of these features bounce solar radiation back into space before it can be absorbed and converted into heat. Earth's oceans, forests, and dark soil act as thermal sponges, soaking up sunlight and releasing it slowly as warmth. Mars has no such mechanisms. The energy it needs to escape its cold prison simply reflects away, a cosmic rejection of the very warmth that could save it. And then there are the temperature swings themselves, variations so extreme they would challenge any infrastructure we might attempt to build. Imagine constructing habitats, power systems, transportation networks on a world where the temperature might shift 145 degrees Celsius between noon and midnight, between summer and winter. Metals would expand and contract with each cycle, fatiguing and fracturing. Seals would crack. Electronics would fail. Even advanced materials engineered for space exploration would struggle under such relentless thermal stress, measured not in months or years, but across decades and centuries of continuous operation. To truly terraform Mars, to raise its temperature to something resembling Earth's comfortable range, would require energy on a scale that staggers the imagination. We are not speaking of heating a building or even a city. We are speaking of warming an entire planet, of pumping heat into 144 million square kilometers of frozen landscape continuously, indefinitely, until the very rocks themselves begin to release their ancient stores of trapped gases. The energy requirements would dwarf anything human civilization has ever attempted. Some estimates suggest we would need to deploy mirrors in space larger than entire continents, or detonate thousands of nuclear devices to melt the polar caps, or construct fusion reactors numbered in the millions, all running simultaneously for centuries. Even our most optimistic projections of future energy production fall short by orders of magnitude. What took Earth billions of years to develop, a complex, self-regulating temperature system, cannot be replicated on Mars through force of will alone. Our planet's warmth is not an accident. It is the product of geological processes that cycle carbon through rocks and oceans, of life itself, plants and plankton that transformed our atmosphere over eons, of a magnetic field that shields our air from solar wind. of an atmosphere thick enough to distribute heat from equator to pole. These systems did not emerge in decades or centuries. They evolved across deep time, refined through countless cycles of climate change, extinction, and renewal. Mars had its chance at this evolution. Evidence suggests that billions of years ago, when the solar system was young, Mars possessed a thicker atmosphere, flowing water, perhaps even a warmer climate. But that Mars died. Its magnetic field collapsed. Its atmosphere bled away into space. Its water froze and was buried beneath dust. The planet we see today is not a world awaiting transformation. It is a world that has already transformed, from warmth to cold, from wet to dry, from possibility to finality. To terraform Mars is to fight against this planetary death, to attempt to reverse billions of years of thermal entropy with technology that does not yet exist, and energy we cannot generate. The cold is not simply an obstacle, it is a fundamental characteristic of what Mars has become. Heating a planet is not like warming a room. There is no thermostat to adjust, no furnace that can run indefinitely without fuel. In the silence of space, Mars turns beneath its pale sun, its surface temperatures rising and falling in their ancient rhythm, indifferent to human dreams of warming. The cold is patient. It has waited for eons. It can wait longer still. And as we contemplate the frozen, rust-coloured deserts below, we must ask ourselves, are we truly seeking to transform Mars? Or are we simply unwilling to accept that some prisons, even planetary ones, have no key? Beyond the thin atmosphere and frozen surface, Mars harbours an invisible assassin, one that cannot be seen, cannot be touched, but will quietly dismantle every cell in a human body. This is not a distant threat or a theoretical concern. It is a present, constant, and utterly unavoidable reality. Mars is bathed in radiation levels 50 times higher than those on Earth. To walk unprotected on its surface is to invite a slow cellular death. To terraform Mars is not simply to build habitats and grow plants. It is to somehow shield an entire planet from the relentless bombardment of the cosmos itself. And here, we face a truth more uncomfortable than any other. We have no solution. Radiation on Mars arrives from two primary sources, each deadly in its own way. The first is galactic cosmic rays, high-energy particles that have travelled across the universe for millions of years, streaming through space at nearly the speed of light. These particles, mostly protons and atomic nuclei, are remnants of ancient supernova, stellar explosions so violent they flung matter across galaxies. They strike Mars constantly, penetrating deep into the surface, passing through rock, through metal, through flesh. There is no hiding from them, no simple barrier thick enough to stop them completely. The second source is solar particle events, sudden eruptions from the sun that release torrents of charged particles into space. These events are unpredictable and catastrophic. During a major solar storm, radiation levels on Mars can spike to lethal doses within hours. On Earth, we barely notice these events. Our magnetic field deflects them harmlessly into space, creating beautiful auroras instead of deadly exposure. On Mars, there is no such protection. A solar storm on Mars is a silent apocalypse. Invisible waves of energy that would kill an unshielded human in days, if not hours. The difference between Earth and Mars is not merely one of degree, but of fundamental planetary architecture. 4 billion years ago, Mars possessed something Earth still has: a global magnetic field. generated by the churning of molten iron in its core. This invisible shield wrapped around the planet, deflecting cosmic radiation and solar wind, preserving the atmosphere and protecting any potential life beneath. But Mars is a smaller world. Its interior cooled faster. The dynamo within its core ceased, and the magnetic field collapsed. What remained was a naked planet, exposed to the full fury of space. Earth's magnetic field is not a luxury. It is the reason complex life exists here. It is an invisible fortress that has stood for billions of years, bending the trajectories of lethal particles, guiding them safely around our world. Without it, Earth's atmosphere would have been stripped away long ago, just as Mars's was. Without it, life as we know it could never have evolved beyond the simplest microbial forms, hiding deep underground or beneath thick layers of water. Mars lost this protection eons ago, and it cannot be restored. The health consequences of Mars's radiation environment are not speculative. They are well documented from studies of astronauts, nuclear workers, and survivors of radiation exposure on Earth. Long-term exposure to the levels found on Mars would result in a dramatic increase in cancer rates. Every organ, every tissue, every cell would accumulate damage. Over time, DNA strands would break and mismatch during repair. Cellular machinery would falter. The body's ability to regenerate would be compromised at the most fundamental level. But cancer is only the beginning. Radiation exposure causes cognitive decline, a gradual deterioration of brain function that cannot be reversed. Memory falters. Decision-making becomes impaired. The very neurons that define our thoughts and personality are damaged by particles streaming through the brain. Studies on astronauts aboard the International Space Station, shielded far better than any Mars colonist could be, already show measurable cognitive effects from radiation exposure during missions lasting only months. A lifetime on Mars would turn mental decline from a possibility into a certainty. Perhaps most devastating is the impact on reproduction. High radiation environments cause genetic mutations, cellular damage to developing embryos, and reproductive failure. The possibility of raising children on Mars, of establishing a truly self-sustaining colony, becomes not just difficult, but biologically untenable. A civilization that cannot reproduce is not a civilization. It is a temporary outpost, counting down the years until the last generation fades away. The most common proposed solution is to build underground, to tunnel into the Martian crust and live beneath meters of rock and soil, using the planet itself as a radiation shield. And yes, this would work to some degree. Radiation levels underground would be significantly lower, possibly approaching tolerable ranges for human habitation. But this is not terraforming. This is entombment. The dream of Mars is not to live in caves, cut off from the sky, isolated in artificial tunnels that could exist anywhere in the solar system. The dream is to walk freely on the surface, to breathe the air, to build cities beneath open skies. Living underground defeats the entire purpose of choosing Mars. It transforms the vision from planetary settlement to subterranean imprisonment, and the psychological toll of such existence cannot be ignored. Humans evolved beneath open skies, surrounded by natural light, connected to the rhythms of day and night, weather and seasons. Confinement in artificial environments, even well-designed ones, produces measurable psychological stress. Depression, anxiety, and interpersonal conflict increase in isolated, enclosed spaces. Experiments in Earth-based habitats designed to simulate Mars missions consistently reveal these challenges. Now imagine not a months-long simulation, but a lifetime. Not a temporary mission with the promise of return, but permanent exile in underground corridors where the sky is a memory and sunlight a rare luxury. Some propose biological solutions, engineering radiation-resistant organisms, modifying human genetics to better tolerate exposure, creating life forms that can thrive in Mars's hostile environment. These ideas sound promising in theory, but they are scientific fantasies masquerading as solutions. Radiation resistance in organisms like tardigrades or certain bacteria comes with profound biological limitations. These creatures survive through extreme dormancy, slowed metabolism, and DNA repair mechanisms that work only because their biological processes are vastly simpler than those of humans. Translating these adaptations to complex multicellular life, let alone intelligent beings, is not a matter of inserting a few genes. It would require redesigning the fundamental architecture of human biology, creating something that might survive Mars, but would no longer be recognizably human. The ultimate solution, the one that haunts every serious discussion of terraforming Mars, would be to restore the planet's magnetic field, to somehow reignite the dynamo within Mars's core, or to construct an artificial magnetic shield vast enough to protect an entire planet. This is not a challenge of engineering. It is a challenge of planetary-scale physics that borders on the impossible. Restarting a planetary core would require energies beyond our comprehension, technologies that do not exist even in theoretical form. Proposals for artificial magnetic fields involve placing massive superconducting satellites at Mars's Lagrange points, generating fields strong enough to deflect solar wind. Even the most optimistic projections place such technology centuries in the future, requiring resources, energy, and coordination on a scale humanity has never achieved. And so, we return to the invisible killer. Radiation on Mars is not a problem to be solved with better materials or clever design. It is a fundamental consequence of planetary death, the result of a magnetic heart that stopped beating billions of years ago. Mars is a world without protection, a corpse exposed to the endless bombardment of space. To terraform, it is not merely to change its atmosphere or warm its surface. It is to resurrect something that died when Earth was still young, when life here was nothing more than chemical whispers in ancient seas. We stand before Mars with ambition, but the universe answers with physics. And physics, unlike dreams, does not bend to human will. Water is the foundation of life as we know it. It carves landscapes, nourishes ecosystems, and flows through the veins of every living organism on Earth. When scientists discovered vast reserves of water ice on Mars, buried beneath its polar caps and scattered across its frozen soil, excitement surged through the scientific community. Here was the key ingredient, the essential element that could transform Mars from a barren wasteland into a living world. Yet this discovery, promising as it seemed, conceals one of the most insurmountable paradoxes in the entire terraforming dream. Mars has water, abundant water, locked in ice that spans regions larger than continents. But this water exists in a prison of physics, trapped in conditions that render it nearly useless for sustaining life or creating the oceans that terraforming requires. The first barrier is not a lack of water, but the fundamental nature of how water behaves on Mars. On Earth, water transitions smoothly between three states: solid ice, liquid water, and gaseous vapor. This elegant dance between phases is what creates our weather, our oceans, our rain, the entire hydrological cycle that makes our planet habitable. But on Mars, this dance is broken. The atmospheric pressure on the Martian surface averages just 6 millibars, less than 1% of Earth's pressure. This seemingly technical detail creates a catastrophic problem known as the triple point paradox. At Mars's low pressure, liquid water cannot exist in a stable state. When ice warms on the Martian surface, it does not melt into liquid. It sublimates, transforming directly from solid to vapor, skipping the liquid phase entirely. Water on Mars cannot pool. It cannot flow. It cannot form the lakes, rivers, and oceans that life requires. The moment ice begins to warm, it vanishes into the thin atmosphere as vapor, leaving nothing behind but dust. This is not a temporary obstacle or an engineering challenge to be overcome with better heating systems. This is physics asserting its absolute authority. To create liquid water on Mars, you must first create an atmosphere thick enough to allow water to exist in liquid form. But as we have seen, creating and maintaining such an atmosphere on Mars is itself impossible given the planet's lack of a magnetic field and its weak gravity. The water paradox and the atmosphere problem are locked together in a vicious circle. You cannot have liquid water without a dense atmosphere, and you cannot maintain a dense atmosphere without solving problems that have no solution. The ice on Mars, vast as it is, remains forever trapped in a state that cannot support the water cycle necessary for life. Even if we could somehow solve the pressure problem, the water itself presents another deeply troubling obstacle. Martian soil is contaminated with perchlorates, toxic chemical compounds that permeate the regolith across the entire planet. These perchlorates dissolve readily in water, meaning any ice melted from Martian soil would be poisoned from the moment it liquefied. Perchlorates are not merely unpleasant. They are actively toxic to most Earth organisms, interfering with thyroid function and disrupting biological processes at the cellular level. Purifying water contaminated with perchlorates requires sophisticated filtration systems, chemical processing, and enormous energy inputs. Doing this for a few liters in a laboratory is manageable. Doing it for billions of gallons, enough to create rivers and lakes across an entire planet, crosses into the realm of impossibility. The water locked in Mars's ice is not pure mountain spring water waiting to be released. It is toxic sludge that would poison any ecosystem attempting to take root. The energy requirements compound the paradox further. Mars is cold, brutally cold, with average temperatures hovering around -80 degrees Fahrenheit. Melting ice requires energy. Keeping water liquid in an environment where temperatures plummet far below freezing every single night requires continuous massive energy inputs. On Earth, the sun provides this energy freely, warming oceans and maintaining liquid water across vast expanses without human intervention. On Mars, sunlight is weaker, reaching the surface with less than half the intensity it has on Earth. To melt the polar ice caps alone would require energy expenditures equivalent to humanity's total current power generation for centuries, and that is just to melt the ice once. Maintaining liquid water across a planet that desperately wants to freeze requires a constant battle against thermodynamics, a battle that can never be won without first solving the temperature and atmosphere problems that have no solutions. Creating a functioning water cycle demands far more than simply melting ice. On Earth, water evaporates from oceans, rises into the atmosphere, condenses into clouds, and falls as rain, continuously cycling through the biosphere in a self-sustaining system powered by solar energy and regulated by atmospheric pressure and temperature. This cycle depends on a complex interplay of systems: a dense atmosphere to hold water vapor, moderate temperatures to maintain liquid water, weather patterns to distribute moisture, and a magnetic field to protect the entire system from solar wind. Mars lacks all of these prerequisites. Without them, any water released into the Martian environment would either freeze solid, sublimate into space, or both. There is no pathway to creating a hydrological cycle without first terraforming the entire planet, and as we have seen, terraforming itself is impossible. The cruelest irony of Mars's water paradox lies written in the planet's ancient geology. Dried river valleys snake across the Martian surface. Mineral deposits that form only in the presence of liquid water scatter across ancient lake beds. Deltas frozen in time mark where rivers once emptied into vast seas. Mars once had oceans. Billions of years ago, water flowed freely across the surface, carving canyons and filling basins in a world that might have resembled early Earth. But Mars lost its oceans through the same relentless processes that would defeat any terraforming attempt. Its magnetic field collapsed. Its atmosphere was stripped away by solar wind. Its temperature plummeted as the greenhouse gases that once warmed it vanished into space. The water that once danced across the surface was either lost to space or driven underground, locked into permafrost that can never again sustain a living world. Mars is not a planet waiting to be terraformed. It is a cautionary tale written in ice and dust, a demonstration of what happens when the delicate balance of planetary systems collapses. The water on Mars exists as a memorial to what once was, and a reminder of what can never be again. We can see the ice, we can measure it, we can even dream of melting it. But the physics of Mars, the low pressure, the toxic soil, the brutal cold, the absent magnetic field, ensure that this ice will remain forever trapped. Not by lack of technology or insufficient will, but by the fundamental laws of nature that govern how planets work and how water behaves. The dream of Martian oceans crashes against the unmovable reality that the conditions necessary for those oceans to exist are the very conditions Mars has lost and can never regain. Here, in the frozen wastes of a dead world, water itself becomes a paradox, abundant yet useless, present yet inaccessible, a tantalizing promise that can never be fulfilled. The ice remains, silent and still, waiting for oceans that will never come. Beneath the surface of Mars lies not soil, but a chemical wasteland. The red dust that covers the planet appears innocent from orbit, but at the molecular level, it is hostile to life in ways we are only beginning to understand. Mars may have water ice and carbon dioxide. It may have minerals and rock, but it does not have soil. And without soil, nothing grows. Not gardens, not forests, not the foundation of a living world. On Earth, we take soil for granted. We walk upon it, build upon it, plant seeds within it, and expect life to emerge. But soil is not simply ground-up rock. It is alive. Every handful of Earth's soil contains billions of microorganisms, fungi, bacteria, nematodes, and countless microscopic creatures working in concert to break down organic matter, cycle nutrients, and create the conditions for plants to thrive. Soil is an ecosystem unto itself, a biological engine that took billions of years to evolve. Mars does not have this. What Mars has is regolith, a lifeless powder of pulverized minerals, and the difference between regolith and soil is the difference between dust and life itself. The Martian regolith is not just devoid of biology, it is actively toxic. Scattered throughout the red surface are perchlorates, chemical compounds containing chlorine and oxygen that exist in concentrations far beyond anything found naturally on Earth. These perchlorates make up anywhere from 0.5% to 1% of the Martian surface by weight. That may sound small, but it is catastrophic for agriculture. Perchlorates are poison. They disrupt thyroid function in animals. They inhibit plant growth by preventing cells from taking up iodine. They are so reactive that they can spontaneously combust organic material under the right conditions. To grow food on Mars is not simply to plant seeds in alien dirt. It is to attempt agriculture in a medium laced with industrial-grade oxidizers. Some have proposed washing the regolith to remove perchlorates, extracting them through chemical processing or biological filtration. But consider the scale. To terraform Mars, to create arable, land across even a fraction of its surface would require processing billions upon billions of tons of toxic regolith. It would demand constructing massive filtration facilities, transporting water in quantities that Mars does not possess in liquid form, and doing so continuously for centuries. And even if the perchlorates were removed, what remains is still not soil. It is sterile mineral powder, devoid of the organic matter and microbial life that make Earth's soil fertile. Earth's soil is built upon death. Leaves fall. Animals decompose. Microorganisms consume organic matter and release nutrients. Nitrogen-fixing bacteria pull nitrogen from the atmosphere and convert it into forms that plants can absorb. Fungi form symbiotic relationships with plant roots, extending their reach and enhancing nutrient uptake. Earthworms tunnel through the ground, aerating it, mixing it, transforming it into a living substrate. This is the nitrogen cycle, the carbon cycle, the intricate dance of decomposition and renewal that has unfolded on Earth for billions of years. Mars has none of this. Its atmosphere contains almost no nitrogen in a usable form. Its surface has no decomposing leaves, no bacteria to fix elements, no worms to turn the soil. Without these cycles, without this invisible web of biology, there is no mechanism to create or sustain fertility. Heavy metals further contaminate the Martian surface. Iron oxides give Mars its red hue, but the regolith also contains elevated levels of chromium, nickel, and other metallic elements that would be toxic in concentrated exposure to most Earth organisms. Oxidizing compounds, formed by the interaction of solar radiation with the atmosphere and surface, actively break down organic molecules. If you were to place a seed in Martian regolith, even with water and warmth, it would not sprout into a thriving plant. It would struggle against a medium that chemically degrades the very compounds it needs to grow. Mars does not simply lack life. Its surface actively resists it. Some experiments have shown limited success growing plants in simulated Martian soil, controlled environments where scientists carefully adjust chemistry, add fertilizers, and introduce Earth microbes to assist growth. These experiments are hopeful. They demonstrate that with enough intervention, some hardy species can survive in treated regolith under artificial conditions. But these are laboratory demonstrations, small-scale efforts conducted within greenhouses, where every variable is managed, where humans provide constant care, nutrients, and biological assistance. They do not scale. Growing a few plants in a controlled dome is not the same as transforming an entire planet into a garden. The gap between a greenhouse experiment and planetary-scale agriculture is not measured in effort alone. It is measured in geological time. To build true soil on Mars would require introducing not just plants, but entire ecosystems. Bacteria, fungi, decomposers, nitrogen fixers, organisms that can survive the hostile chemistry, reproduce in the cold, and begin the slow work of breaking down minerals and cycling nutrients. Even under ideal conditions on Earth, soil formation is measured in centuries. In harsher climates, it can take thousands of years for a few inches of fertile topsoil to develop. On Mars, a world without liquid water, without atmospheric protection, without an existing biosphere to seed the process, soil formation would take not centuries, but potentially millions of years. And that assumes we could even establish the initial biological foothold, an assumption that may itself be impossible given the surface toxicity and radiation exposure. Earth's soil is not an invention. It is an inheritance, the product of billions of years of evolution, extinction, adaptation, and biological collaboration. Every forest floor, every grassland, every field of crops rests upon a foundation built by ancient microbes, by the first lichens that clung to bare rock, by generations of life living, dying, and enriching the ground beneath them. We did not create this system. We were born into it, and we cannot easily replicate it elsewhere, no matter how advanced our technology becomes. The dream of Martian farms, of vast agricultural plains stretching beneath domed skies, assumes that soil is a simple substrate, something that can be manufactured or imported with enough ingenuity. But soil is not inert. It is alive. It breathes. It evolves. It responds to the organisms within it, and they in turn depend upon its chemistry and structure. To terraform Mars is not merely to warm the planet or thicken its atmosphere. It is to create, from nothing, the biological foundation that every living world requires. And that foundation, built upon countless invisible partnerships between microbes and minerals, between death and renewal, cannot be rushed. Without soil, there are no crops. Without crops, there is no sustaining a human population. Without a self-sustaining biosphere, every meal on Mars would need to be imported, grown hydroponically in artificial environments, or synthesized through industrial processes. Mars could support research outposts, small habitats where food is carefully cultivated in controlled systems. But a living world, a second Earth, requires more than domes and greenhouses. It requires the ground itself to be alive. And the ground of Mars is not alive. It may never be. The regolith of Mars is a reminder that planets are not blank canvases. They are the result of billions of years of chemistry, geology, and in Earth's case, biology. We cannot paint life onto a dead world simply by wishing it so. Soil is not dirt. It is history. And Mars, for all its allure, has no history of life to build upon. Only dust. Only silence. Only the deep, unbroken stillness of a world that has never known the quiet hum of microbial transformation beneath its surface. Even if we could solve the atmosphere retention problem, the radiation shielding, and the temperature trap, we would still face a challenge so fundamental it exposes the entire terraforming dream as fantasy. Where would the materials come from? Not the machines, not the technology, but the raw elements themselves, the gases, the nitrogen, the water vapor, the trillions upon trillions of tons of matter required to transform a dead world into a living one. To terraform Mars is not simply to build something. It is to transport the mass equivalent of entire planetary atmospheres across millions of miles of space. And when we calculate what this actually requires, the numbers do not inspire confidence. They inspire disbelief. Let us begin with the atmosphere. Earth's atmosphere weighs approximately 5 quadrillion tons. 5,000 trillion tons of gas pressing down upon our surface, creating the pressure and density that allows liquid water to exist and life to flourish. Mars currently has an atmosphere that weighs roughly 25 trillion tons. It needs 200 times more gas just to reach pressures comparable to Earth. This means we would need to find, transport, or create nearly 5 quadrillion tons of atmospheric gases and deliver them to a planet that cannot hold on to them without an artificial magnetic field we do not know how to build. But the challenge is not merely one of quantity, it is one of composition. Mars does not simply need more air, it needs the right kind of air. And this is where the impossibility becomes absolute. Nitrogen, the silent, inert gas that makes up 78% of Earth's atmosphere. We breathe it with every breath, though our bodies do not use it. Plants require it to grow. Bacteria convert it into usable compounds through nitrogen fixation, creating the foundation of all terrestrial ecosystems. Without nitrogen, there is no agriculture, no biosphere, no sustainable life as we know it, and Mars has almost none. Current estimates suggest Mars contains less than 3% nitrogen in its thin atmosphere. Even if we could extract every molecule of nitrogen from Martian soil, ice, and air, we would have only a tiny fraction of what is needed. The nitrogen simply is not there. It never was. Mars lost it billions of years ago, blown away by solar wind after its magnetic field collapsed, stripped molecule by molecule into the void of space. So where would we get it? Proposals exist, floating in the optimistic fringes of scientific imagination. Redirect comets, some say. Capture nitrogen-rich bodies from the outer solar system and crash them into Mars, delivering their frozen payloads over centuries. Mine the moons of Jupiter or Saturn, others suggest. Extract nitrogen from Titan's atmosphere, where it exists in abundance, and transport it across 1 billion miles of darkness. These are not engineering proposals. They are science fiction masquerading as possibility. To redirect a single comet requires energy, expenditures beyond our current capabilities. To redirect thousands of comets, enough to deliver the necessary nitrogen, would require a sustained effort spanning millennia and an energy output exceeding the total power consumption of human civilization by orders of magnitude. We are not talking about difficult projects. We are talking about efforts that would require us to become a Type 2 civilization on the Kardashev scale, capable of harnessing the entire energy output of the sun. And even if we possessed such power, the logistics remain staggering. Comets do not arrive on schedule. Their orbits are chaotic, their trajectories unpredictable. Capturing one safely, altering its course without fragmenting it, ensuring it impacts Mars at the correct angle and velocity to deliver gases rather than vaporize them into space. Each step multiplies the complexity. Each variable introduces new failures. The timeline for such an endeavor, even under the most optimistic assumptions, stretches beyond 1,000 years. Generations would live and die waiting for nitrogen that might never arrive. But let us imagine for a moment that we solve the nitrogen problem. That through some extraordinary breakthrough, we find a way to deliver the necessary gases to Mars. We still face the energy requirements. Terraforming is not a passive process. It requires constant input, continuous maintenance, perpetual effort to sustain an atmosphere that wants to escape, to warm a planet that radiates heat into space, to shield a surface from radiation that pours down without mercy. Conservative estimates suggest that terraforming Mars would require an energy output equivalent to detonating thousands of nuclear weapons every single day for centuries. Others propose massive orbital mirrors to focus sunlight, greenhouse gas factories operating at scales never before conceived, or networks of automated machines covering the entire planet, working ceaselessly to maintain atmospheric pressure. Each of these systems would consume energy measured not in gigawatts or terawatts, but in petawatts, powers of 10 that dwarf every power plant, every generator, every energy source humanity has ever constructed, combined. The cost, measured in economic terms, becomes absurd. Estimates range from hundreds of trillions to quadrillions of dollars, numbers so large they lose meaning. The entire global economy of Earth, directed solely toward transforming Mars for 1,000 years, might not be sufficient. And for what return? A planet that remains weaker than Earth in gravity, colder in climate, more hostile to life. A world that would still require domes, still demand artificial support systems, still threaten its inhabitants with dangers that do not exist on the planet we already possess. And here, we must confront the most uncomfortable question of all. Why? Why expend resources on a scale never before imagined to terraform a world that resists transformation at every turn, when those same resources could solve Earth's problems 1,000 times over? The energy required to warm Mars could power carbon capture systems that reverse climate change on Earth. The materials needed to build Martian infrastructure could construct rotating space habitats, artificial worlds that spin to create gravity, that can be positioned anywhere in the solar system, that do not depend on the geology of a dead planet. O'Neill cylinders, Stanford Torrey, structures conceived in the 1970s that remain more practical than terraforming. These habitats could house millions, spinning in the void, their interiors designed with breathable air, comfortable gravity, protection from radiation, and climates of our choosing. They do not require us to alter planets. They do not demand that we transport atmospheres across space or mine distant moons. They need only materials from asteroids, abundant and accessible, floating in the belt between Mars and Jupiter, waiting to be harvested. The resources required to terraform Mars would be better spent building hundreds, perhaps thousands of such habitats. Entire civilizations could flourish in space, independent of planetary surfaces, free from the tyranny of gravity wells and atmospheric loss. And unlike Mars, these structures could be expanded, modified, relocated. They are not bound to geology. They are bound only to human ingenuity. The resource impossibility is not a challenge to be overcome. It is a wall that reveals the fundamental flaw in the terraforming dream. Mars does not merely resist transformation, it makes transformation irrational. The materials do not exist. The energy cannot be supplied. The timeline exceeds the span of empires. And the cost, both economic and existential, dwarfs any conceivable benefit. To terraform Mars is to fight against the universe itself. And the universe, patient and immense, does not yield to ambition alone. It yields only to reality. And the reality is clear. Mars will not become Earth. It cannot. The resources required do not exist in forms we can access. The effort demanded exceeds what our civilization can provide. And the question we must ask is not how to make it possible, but why we are unwilling to accept that some dreams, no matter how compelling, were never meant to be realized. Beyond the atmospheric failures, beyond the radiation bombardment, beyond even the toxic soil, there exists a problem on Mars that we cannot engineer away. It is fundamental. It is absolute. It is written into the very fabric of the planet itself. Mars is too small, and with that single truth comes a gravitational consequence that may render all dreams of permanent human habitation nothing more than beautiful impossibilities. Gravity on Mars is only 38% of what we experience on Earth. When we imagine walking on the Martian surface, we picture graceful, bounding movements, like astronauts on the Moon, leaping across rust-colored plains with ease. It seems almost magical, liberating, as though Mars offers us a lighter existence. But gravity is not a feature we can celebrate. It is a force our bodies were built by, shaped across millions of years of evolution. Every bone, every muscle, every heartbeat has been calibrated to function under Earth-specific pull. On Mars, that calibration begins to fail, not suddenly, but slowly, insidiously, like a clock that loses seconds each day until time itself becomes unreliable. The human body, when removed from Earth's gravity, begins to dismantle itself. Astronauts aboard the International Space Station experience this firsthand. Despite exercising for hours each day, despite carefully designed resistance machines and strict medical protocols, they still lose bone density at a rate of 1 to 2% per month. Their muscles atrophy. Their cardiovascular systems, no longer needing to pump blood upward against gravity, begin to weaken and adapt to a reality where effort is no longer required. After 6 months in space, astronauts return to Earth, unable to stand without assistance. Their bodies must relearn what it means to be heavy, to be pulled downward, to exist in the world that created them. But the ISS is not Mars. The ISS orbits in microgravity, essentially weightlessness. Mars offers 38% of Earth's pull, a middle ground that may seem like a compromise, but could prove even more insidious. It is enough gravity to make you feel grounded, to walk rather than float, yet not enough to maintain the biological systems that keep humans alive and healthy over decades. The question is not whether Mars's gravity will affect the human body. The question is whether those effects are survivable, reversible, or catastrophic. Studies suggest that even Mars's partial gravity will lead to irreversible bone loss, particularly in weight-bearing structures like the spine, hips, and legs. Unlike astronauts who return to Earth after months and begin the painful process of recovery, colonists on Mars would have no Earth to return to. Their bones would continue thinning year after year, becoming brittle and fragile. Fractures would become common. Osteoporosis, a condition typically associated with old age, would strike the young. A Martian colonist in their 30s might have the skeletal structure of an elderly person, and no amount of calcium supplements or exercise could fully counteract the planet's weak pull. Muscle atrophy would be equally relentless. The heart, a muscle that has spent billions of evolutionary years learning to pump blood upward through a body standing on Earth, would weaken in Mars's reduced gravity. Blood pressure would drop. The cardiovascular system would recalibrate to the lower demands of a lighter world. Over time, colonists might find themselves unable to perform even basic physical tasks. Their bodies, adapted to Mars, would become incompatible with Earth. The journey between worlds would no longer be a matter of distance, but of biology. A person who spent years on Mars might never be able to return home, not because of technology or cost, but because their own body would collapse under the weight of Earth's gravity. Then there is the question no one can answer, the question that haunts every vision of Martian cities and multi-generational colonies. Can a human child develop normally in 38% gravity? We do not know. No human has ever been conceived, gestated, or born anywhere other than Earth. The process of pregnancy is profoundly sensitive to gravity. The placenta must deliver nutrients upward. The fetus must develop bones and muscles in an environment that constantly pulls downward. Amniotic fluid, circulation, cellular development, all of these occur within the invisible scaffolding of Earth's 1G environment. On Mars, everything changes. Would a fetus develop properly? Would bones form with the necessary density? Would the cardiovascular system learn to pump with enough strength? Or would Martian-born children emerge weak, fragile, their bodies built for a world they can never leave? Some scientists speculate that pregnancy might be impossible in low gravity, that miscarriages would be common, that developmental defects would render multi-generational colonization a biological dead end. Others believe children could be born, but would face a cruel reality. They would be Martians, not by choice, but by the unchangeable physics of their birth. Their bodies would be adapted to Mars's weak pull, and Earth, the cradle of humanity, would be forever forbidden to them. A child born on Mars could never visit the oceans, never walk through forests, never feel the full weight of their own existence under the sky that made their species. They would be exiles from their own evolutionary home. This is the cruelest truth of the gravity problem. Unlike atmospheric pressure, which could theoretically be contained within domes, unlike radiation, which might be shielded with enough material, gravity cannot be engineered. We cannot add mass to Mars. We cannot spin the planet faster or compress its core to increase its pull. Gravity is a direct function of mass, and Mars's mass is fixed, unchangeable, written into the structure of the solar system billions of years ago. No technology, no matter how advanced, can alter this fundamental property. We can build cities on Mars. We can grow food in greenhouses. We can extract water from ice and generate oxygen from the atmosphere. But we cannot make Mars pull harder. We cannot make it hold us the way Earth does. Some propose rotating habitats, enormous spinning cylinders that create artificial gravity through centrifugal force. But these are not solutions for a planet. They are enclosed environments, space stations built on the surface, another layer of separation between humans and the world they claim to inhabit. If colonists must live in spinning tubes to maintain their bone density, are they truly living on Mars, or simply using Mars as a foundation for structures that keep them isolated from the planet itself? The gravity problem is not a challenge to be overcome. It is a boundary, a line drawn by physics itself. It suggests that human bodies, shaped by Earth's pull over millions of years, may not be compatible with permanent life on Mars. We can visit. We can stay for months, perhaps even years, knowing that damage is accumulating but accepting it as temporary. But to live there, to raise children there, to build civilizations that last centuries, the gravity problem whispers that this may not be possible, not without fundamentally altering what it means to be human. In the stillness of the Martian night, beneath a sky filled with stars, gravity continues its silent work. It does not roar like a storm. It does not burn like radiation. It simply pulls, gently, persistently, not quite enough to hold us the way our home world does. And in that gentle, insufficient pull lies a truth we are only beginning to understand. Some problems cannot be solved. Some forces cannot be changed. Some dreams, no matter how beautiful, cannot survive the unchanging laws of the universe. Perhaps the greatest obstacle to terraforming Mars is not technical or physical, but philosophical. We have been asking the wrong question. Not, can we terraform Mars, but rather, should we? And more importantly, what if there are better ways to secure humanity's future among the stars? The dream of Mars has captivated us precisely because it resembles Earth just enough to seem attainable. Yet, in our fascination with the red planet, we may have overlooked solutions that are not just more feasible, but profoundly more elegant. Alternatives that do not require us to wage a millennia-long war against an entire planet's physics. Solutions that exist not on hostile surfaces, but in the careful engineering of artificial worlds, or in places far closer than we ever imagined. High above Earth, suspended in the darkness beyond our atmosphere, there exists a vision first conceived not by science fiction writers, but by physicists. The O'Neill cylinder. Named after Princeton professor Gerard K. O'Neill, these structures represent a fundamentally different approach to space colonization. Rather than trying to reshape planets that resist our presence, we build worlds from nothing, engineered precisely for human life. An O'Neill cylinder is a massive rotating habitat, typically imagined as two counter-rotating cylinders, each perhaps 20 miles long and several miles in diameter. As the cylinders spin, centrifugal force creates artificial gravity along the inner surface. People would live on the inside walls of these cylinders, looking up to see not sky, but the opposite side of their world, dotted with forests, lakes, and cities curving overhead. The rotation speed determines gravity. Spin faster, and weight increases. Spin slower, and it decreases. For the first time in space exploration, gravity becomes not a constraint we must accept, but a variable we control. The advantages are profound. Unlike Mars, where radiation pours endlessly through a thin atmosphere, O'Neill cylinders can be shielded with layers of rock and metal mined from asteroids. The hull becomes Earth's magnetic field in miniature, deflecting cosmic rays and solar particles with engineered precision. Inside, atmospheric pressure, temperature, and composition can be set to match Earth exactly. Not the thin toxic air of terraformed Mars centuries from now, but breathable atmosphere from day one. Sunlight can be directed inward through massive mirrors, creating day and night cycles of any length desired. Agriculture becomes not a struggle against toxic soil, but controlled farming in nutrient-rich environments optimized for growth. Water, once established in the system, recycles endlessly. Nothing is lost to a planetary surface. Everything remains contained, managed, sustained. These habitats could be built near Earth, making travel a matter of days rather than months. Or they could be positioned at stable Lagrange points, cosmic harbours where gravity balances perfectly. They could even accompany mining operations in the asteroid belt, mobile cities that follow resources rather than remaining fixed to barren ground. Yet there is another alternative, one that seems paradoxical at first. A planet we have long dismissed as inhospitable may, in fact, be more welcoming than Mars. Venus, shrouded in sulfuric acid clouds and surface temperatures hot enough to melt lead, seems like the last place humanity should consider. But at an altitude of 50 kilometers above Venus's hellish surface, conditions become surprisingly Earth-like. Here, in the Venusian cloud layer, atmospheric pressure matches Earth at sea level. Temperatures hover around a comfortable 60 to 70 degrees Fahrenheit. The atmosphere, though composed primarily of carbon dioxide, is dense enough that breathable air would actually be a lifting gas. Habitats filled with oxygen and nitrogen would float naturally like balloons in Earth's sky. Unlike Mars, where every structure must be pressurized against near vacuum, Venusian cloud cities would exist in pressure equilibrium with their surroundings. A puncture would not explosively decompress, but simply allow gradual mixing. Venus offers something else Mars cannot: protection from radiation. The thick atmosphere absorbs harmful particles more effectively than Mars ever could. Solar panels would generate more power here than anywhere else in the inner solar system except Mercury. And while Venus's surface may be unreachable, the vast cloudscape offers territory larger than all of Earth's continents combined. Cloud cities on Venus, rotating cylinders in Earth orbit. These alternatives force us to reconsider our assumptions. But there is another option, one so obvious we often overlook it. The Moon. Earth's ancient companion sits just 3 days away by conventional spacecraft. Unlike Mars, where rescue missions take years to organize, lunar colonists would live within reach of help. Communication delays, which plague Mars missions with 20-minute round trips, last only seconds from the Moon. Resources can be exchanged with Earth efficiently. Technology can be tested, refined, and upgraded continuously, rather than waiting years between missions. The Moon offers something else: helium-3, a rare isotope that could fuel fusion reactors if we ever perfect that technology. Lunar soil can be processed into oxygen and construction materials. The far side of the Moon, shielded from Earth's radio interference, could host astronomical instruments of unprecedented sensitivity, observatories that see deeper into space and time than anything possible on Earth. Most importantly, the Moon is a proving ground. If we cannot sustain civilization on the Moon, just 3 days from home, what makes us think we can sustain it on Mars, 9 months away? Yet perhaps the most important alternative has been with us all along. Earth, the only planet in the known universe already terraformed for human life. A world with breathable atmosphere, protective magnetic fields, abundant water, and complex ecosystems that have evolved over billions of years. We speak of terraforming Mars while Earth's climate destabilizes, while oceans acidify, while species vanish at rates not seen since the age of dinosaurs ended. The resources required to terraform Mars, if such a thing were even possible, would dwarf anything humanity has ever attempted. Trillions upon trillions of dollars, millions of tons of materials, countless hours of labor across centuries. What if those resources were directed instead toward preserving and restoring Earth, toward carbon capture, renewable energy, ecosystem restoration, and sustainable development? We already live on a terraformed planet. Perhaps we should focus on keeping it that way. This raises the deeper question: why do we want to terraform Mars at all? Is it adventure, the human drive to explore and conquer new frontiers? Is it insurance, a backup location in case Earth becomes uninhabitable? Or is it escape, a desire to flee the problems we've created rather than solve them? If the answer is adventure, then Mars as a research outpost fulfills that need. Scientists exploring an alien world, unraveling geological mysteries, searching for signs of ancient life. This Mars is achievable within our lifetimes, not centuries from now. If the answer is insurance, then O'Neill cylinders and lunar colonies provide redundancy far more quickly and reliably than terraforming ever could. And if the answer is escape, then we must confront an uncomfortable truth. The problems that threaten Earth, climate change, resource depletion, social instability, will follow us to Mars. We cannot terraform a planet if we cannot first learn to sustain civilization on the one planet already designed for us. The scientific value of Mars is immense, but it exists, whether we terraform or not. A network of research stations, exploring, analyzing, discovering, contributes more to human knowledge than a centuries-long engineering project that may ultimately fail. Perhaps our future is not on planetary surfaces at all. Perhaps humanity's destiny lies in orbit, in the spaces between worlds, in rotating habitats where we craft our own gravity, our own atmosphere, our own perfect environments, in floating cities above Venus where clouds become foundations, on the moon where Earth always hangs in the sky, a reminder of home just 3 days away. The universe is vast beyond comprehension, filled with opportunities we are only beginning to recognize. Mars will always be there, a world to study, to visit, to learn from. But the dream of terraforming, of reshaping an entire planet through brute force engineering, may be a dream we need to set aside, not because we lack courage, but because we have gained wisdom. Our future among the stars does not require us to recreate Earth elsewhere. It requires us to carry Earth with us, in habitats of our own design, in technologies yet to be perfected, in the knowledge that sometimes the best solution is not to change the universe, but to change our approach to it. But this realization is not a defeat. It is a compass pointing us toward destinations we can actually reach. To understand what is impossible is not pessimism, it is wisdom. It allows us to stop chasing mirages in the Martian dust and instead direct our resources, our brilliance, and our ambition towards solutions that exist within the laws of nature as we know them. Mars remains profoundly valuable. Its rusty deserts hold secrets about planetary evolution, about the possibility of ancient life, about the violent youth of our solar system. Small research bases, protected habitats for dozens or perhaps hundreds of scientists, these are achievable and worthwhile. Mars can become humanity's greatest laboratory, a place where we test our technology and expand our knowledge without pretending it will ever become a second Earth. There is nobility in exploration without colonization, in understanding without conquest. Perhaps the true frontier is not beneath us on planetary surfaces, but around us in the vast expanse of space itself. Rotating habitats in orbit, where gravity is created by spin rather than borrowed from dying worlds. Stations at Lagrange points, where solar energy flows without atmospheric interference. Settlements in the asteroid belt, where resources drift freely and construction materials outnumber the grains of sand on Earth. These megastructures obey physics rather than fight it. They can be built with the materials and energy actually available to us, expanded module by module, generation by generation. The universe is not silent about what it will allow. Mars speaks clearly through its thin air and frozen ground. It tells us, I am a museum now, not a home. And if we listen, if we accept what The evidence reveals, rather than what our dreams demand, we might discover that the cosmos offers alternatives far more magnificent than a resurrected Mars could ever be. We stand at a threshold where fantasy and engineering must part ways, where the romantic vision of walking unprotected through Martian valleys gives way to the harder, truer vision of humanity thriving in places we build ourselves, sheltered by our own ingenuity, rather than hoping a dead planet will come back to life. If this journey through harsh realities has sparked something in you, whether wonder or disagreement or simply the desire to know more, let us know in the comments below. Tell us where you're listening from, whether you're drifting towards sleep under Earth's protective magnetosphere or pondering these questions under distant skies. Subscribe to continue exploring the universe as it truly is, not as we wish it to be. Because in the end, understanding our limitations is the first step toward transcending them. The stars remain, the void awaits, and humanity's future, if we are wise enough to embrace reality while reaching upward, may be more extraordinary than any terraformed world we once imagined. Some dreams must die so that greater ones can be born.